Okay, so this is the midterm 2 for fall 2022 of MA 265. So in this first problem, we have this matrix A, and we're asked to find the rank of A and the nullity of A, and find what 5b minus 3a is, where b is a nullity and a is the rank. So the first thing to note is that rank is the number of non-zero rows in the row-reduced echelon form. So that means that, not by non-zero row, I mean that there's no row of only zeros. And then the nullity of A is the number of spanning vectors in the null space of A. So when you see rank nullity in the null space of A, so when you see rank nullity, you can automatically think of the rank nullity theorem, where the rank of A plus the nullity of A equals the number of columns of A. And in this case, the number of columns of A is 5. So first we want to find the rank of A, so we want to find the number of non-zero rows, so we need to do row reduction. I'm going to do row 2 is equal to row 2 minus row 1, and then row 3 equals row 3 minus 2 times row 1. And that will give me 1, 0, 2, 0, negative 1, and then 0, 2, 2, negative 2, 0. And this is 0, 3, 3, negative 3, and 0. Okay, so you can see that this row is just a multiple of this row, so this becomes a row of zeros. And after that, you can see that these two rows are linearly independent because they're not multiples of each other. So this means that we have two non-zero rows. So our rank is 2, and that means the rank plus the nullity is equal to 5, which means that the nullity is going to be 3. And you can also see that because the nullity is the number of spanning vectors. So here we have 2 pivot entries, and the other variables here are free variables, so then you would have 3 spanning vectors to define your matrix. So, or your system is a better way of saying it, I think. So now we know that A is equal to 2, and then B is equal to 3. So we have 5 times 3, 5b minus 3a is 5 times 3 minus 3 times 2, which is 15 minus 6, which is 9. So the answer is C. Okay, in this problem, we have these 3 vectors, and the last entry in the last vector, we don't know the last entry. So we want to find when this is a basis, this set of vectors is a basis for R3, and what conditions that requires for C. So when you see a basis, you know that these, first of all, there are 3 vectors, so that means that all 3 vectors have to be linearly independent, because we have 3 vectors span R to the 3. So you have a minimum of 3 vectors needed to span R to the 3. So what you can do here is you can do the test for linear independence, where you want to make sure that, for example, I have C1 times U plus C2. I realize this notation of C's is a bit weird, but these C1, C2, and C3s are not equal to C, like this. So the test for linear independence says that the only way that you can make a linear combination of these 3 vectors equal 0 is if C1, C2, and C3 are equal to 0. So what you can do is you can write this in the augmented matrix form, right? So if we expand this out, we get 2C1 plus 3C2 plus C31, 2C1 plus 3C2 plus C3 equals 0. And so when you write that in augmented matrix form, you have 2, 3, 1, 0, 1, negative 1, and 1, 0, C. Because this is if we just have something like this here. That's equal to 0, 0, 0. And so now that we have this, we just need to row reduce to see that the resulting pivot entries are that there are no free variables in this system. So let's do some row reduction. And then we have the zeros. And I'm going to do row 1 equals row 1 minus 2 row 3. And that equals 0, 3, 1, then 0, 1, negative 1, and then 1, 0, C. Oh, oops, C minus 2. Oh my goodness. Okay, so, wait, what am I doing? Okay, hold on. Okay, so row 1 is equal to row 1 minus 2 times row 2. So 0, 3, and then 1 minus 2c. Okay, this is the result of that row operation. And then I'm going to I want to get rid of this value, this 3, make that a 0. So I'm going to do row 1 equals row 1 minus 3 times row 2. And that will give me 0, 0, 1 minus 2c plus 3, which is 4 minus 2c, equal to 0, 0, 0, 0, 1, negative 1, and then 1, 0, c. So at this point we can kind of pause and think about what we've gotten here. So I guess for clarity, I'll move row 1 to the top. I'll exchange these two rows so it's a bit clearer. But you can see that at the very bottom we have a row of what could potentially be a row of zeros if c is equal to 2. So this doesn't necessarily matter because we have a pivot. We have two pivot entries here. But we know that if we want this to be linearly independent, then this variable, this final C3 variable, has to be equal to 0. And if it's not 0, then that means that this set is not linearly independent. And so this cannot be 0 if we want a basis for R3, because that means that these three vectors are not linearly independent. If that's the case, then C cannot be equal to 2. And so our answer is 2. And this is just a test for linear independence that we've done in this row reduction process. So in this statement we have, in this question we have which of the following statements are true. In the first statement we have if ax equals lambda x for some vector x, then lambda is an eigenvalue of a. So this initially seems correct because this is kind of the definition of an eigenvalue, but the key phrase is some vector x, and so this is a bit weird because if you imagine that x is equal to 0, then obviously ax equals lambda x because 0 equals 0. That means your lambda could be any number, and that means you would have infinite eigenvalues, which is obviously not the case. And so this vector x needs to be non-zero. So it's too vague of a statement by saying some vector x because that vector could be 0, in which case lambda wouldn't be an eigenvalue of a. So this statement is false. In part B we have if v is an eigenvector corresponding to eigenvalue 2, then then negative v is an eigenvector corresponding to eigenvalue negative 2. So in this case, I'm honestly not sure what this means. I'm not sure if it means if a matrix has eigenvalue 2 and negative 2. So just to be safe, I was just trying to come up with counterexamples, and I included both as an eigenvalue. Sorry, I don't know why I can't distinguish between eigenvector and eigenvalue today, but I made a matrix because I think counterexamples are very helpful. Although you could, I think when you work through maybe a few test matrices, you can see like why intuitively this also doesn't make much sense. So I made up this matrix 2, 0, 0, negative 2, and I included 2 and negative 2 as eigenvalues just to be safe, because I wasn't exactly sure what it meant. In this case, if we want to find the eigenvalues, obviously the eigenvalues are 2 and negative 2, And you can again check that by doing the determinant of a minus lambda I and seeing what lambda does that determinant be 0. Anyways, if I look at the eigenvalue of 2, then I get this matrix here when I'm trying to find the eigenvector. So just a quick recap, to find the eigenvector, you want to find when a minus lambda I x equals 0, what x has to be for this to be a valid equation. And that x will be our eigenvector. So in this case, hopefully you can see that our x will be restricted by this variable because that must be equal to 0. So this is 0. And this other entry could be anything. So I can just call this 1. Now, we can also do the same thing for lambda equals -2. And that will give us 4, 0, 0, 0, 0, 0. And now we see that this variable is going to be restricted. It's going to be equal to 0. So when we find the eigenvector, this top variable has to be 0, and this bottom one can be anything because it's a free variable. So I can also call this one 1. So obviously, as you can see, these eigenvectors are not negatives of each other, and so the statement is false. And I think you can also think of it as you're going to have, when you have these eigenvalues, you're going to be, when you're solving for the eigenvectors, you're going to be subtracting them from A, your initial matrix. And when you do that, you're going to have your zeros be in different places. And that generally won't lead to your eigenvectors being a multiple of each other because your zeros will restrict, for example, your zeros here or your 0 here will restrict the value of your eigenvector. So for example, in this case, because there's a 0 here, but then this became our pivot variable, we have a 0 here. Where in contrast, now that the 0 has moved over here and the non-zero pivot entry is here, this 4 here, then your 0 is going to be on the top corresponding to a different variable. And so that's the one way I think you can also think about this, in that the zeros are going to be in different places, so you can't have them be multiples of each other. Okay, so in this statement C, we have if B is invertible, then A and B inverse AB could have different sets of eigenvalues. If you look at this form, you can see that this means that I'm going to call this giant matrix multiplication P, but you can see that A and P are similar, as this is the definition of similar matrices. And we're seeing if there is a different set of eigenvalues for this. And to find the eigenvalues, remember that you're trying to find the determinant of A minus lambda I equals 0, and you solve for lambda. And this means that you're going to have the same characteristic polynomial if you have the same sets of eigenvalues. So we're going to test and see then, is the determinant of A minus lambda I equal to the determinant of P minus lambda I? And this then leads you to think, is A minus lambda I equal to P minus lambda I? And we can do some fun manipulations here, in that P is going to, I've defined it as B inverse AB. So B inverse AB minus, now I do minus lambda I, but I can write this I as B inverse B, right? That just gives me the identity matrix. And, it should be a B. So then I can factor out B inverse and get A minus lambda I times B. And you can see that that means that A minus lambda I and B minus, so you can see now that A minus lambda I and B inverse times A minus lambda I times B are similar, and so they will have the same determinant. So this tells us that same determinant is same. So this verifies this statement, right? Because if we do the determinant of both sides, the determinant of A minus lambda I equals determinant of B inverse times determinant of A minus lambda I times the determinant of B. And the b's will cancel because you're doing the determinant of B inverse times determinant of B. And by determinant properties, that's just 1. So you can see that now this is true statement. And this means that we will have the same characteristic polynomial. And that means that we will then have the same eigenvalues. So just to recap, we found that if we have the same characteristic polynomial for A and B inverse AB, then we'll have the same eigenvalues. And we want to test if this is true or not. And to figure out if it has the same characteristic polynomial, we first figure out if the determinant of A minus lambda I and if the determinant of B inverse AB minus lambda I are the same. So those determinants will certainly be equal if A minus lambda I equals P minus lambda I. But we can do some fancy manipulations and then we get this result here. And then when we take the determinant of both sides, we do find that determinant of A minus lambda I equals the determinant of P minus lambda I, which confirms that we have the same characteristic polynomial, and thus we have the same sets of eigenvalues. So this means that the statement that they have different sets of eigenvalues is false. Okay. And for statement D, we have if lambda is an eigenvalue of A, then lambda squared is an eigenvalue of A squared. So first of all, if we know that lambda is an eigenvalue of A, that means it satisfies this relation. This is a definition of an eigenvalue. Well, then if we try to find A squared, so we can do A times AX, this will give us, substituting this in here, we get A times lambda x. And we can factor out the lambda because lambda is just a scalar, and that gives us lambda ax. But we know that ax equals lambda x, so we get lambda squared x. So yes, this is in fact an eigenvalue of a squared x, because it satisfies this relation. So this is true. And then for part E, we're seeing that if -5 is an eigenvalue of b, then b minus 5i is not invertible. So what this means is that, okay, so first we know that -5 is an eigenvalue of b, so that means that bx equals -5x by definition. And essentially this also tells us that based on the definition of an eigenvalue, the determinant of b minus -5i equals 0. And that means that the determinant of b plus 5i is equal to 0. Okay, so now it's asking about if something is invertible or not. Well, invertible means that your determinant of whatever it is cannot be equal to 0. However, this is saying that b minus 5i is not invertible, whereas this is just saying that b plus 5i will be not invertible. So let me just write that first. Is not invertible because the determinant is equal to 0. But it doesn't say anything about b minus 5i. So this means that this doesn't say anything about b minus 5i, so this statement is false. And if you're not completely convinced, you can also maybe come up with some counterexamples, which is actually pretty, you can come up with a simple one pretty quickly. Like say we have 1 and -5, because these will clearly be our eigenvalues, 1 and -5. Well, if this is b, then b minus 5i is just -4, 0, 0, -10. And the determinant of this, I should write determinant of b minus 5i. So the determinant of this is obviously going to be not 0, which means that this is actually invertible. So that's a counterexample that maybe you could come up with to disprove this statement. So our answer is D. In this problem, we have let P3 be the vector space of all polynomials of degree at most 3.
So this means that we would have, so P3 consists of polynomials, which are in this form, x cubed plus bx squared plus cx plus d, where, a, b, c, d could be 0 because it says the degree at most 3. Which of the following subsets are subspaces of P3? So first of all, the requirement for a subspace first is that there are 3, but the first one is that the 0 vector is within the subspace. So I'll denote the subspace as W. The second requirement is that it is closed under scalar multiplication. So that means if you have some vector v in your subspace, or some element v in your subspace, then c times v is also going to be in your subspace. The third requirement is that if you have a, b, and these are both in your subspace, then a plus b is also in your subspace. So that's meaning it's closed under scalar multiplication, or not scalar multiplication, under addition. So these are the 3 requirements for a subspace, and so we want to check that for each of these sets. So in the first set, we have the set of polynomials that satisfy p0 equals p1. So I don't know why. Okay, there we go. So first of all, we need to figure out, so this is the requirement of this set. So so if, let's just say p of x is our, it should be lowercase. So p of x is our polynomial. So p of 0 is just corresponding to x equals 0. So that is just going to be d. P of 0 is just equal to d. And then p of 1 is when x is equal to 1. So then you just have a plus b plus c plus d as p of 1. So when you have d equals to a plus b plus c plus d. So this just means that a plus b plus c equals 0. And so this is the requirement of this subset. So we want to check if under the conditions for a subspace, so 1, 2, and 3, does this requirement still hold? So in the first case, we were asking if the 0 vector is in this subset. So the 0 vector would just be a, b, c, d equals 0. I don't know why it's being weird today. I don't know what happened, but so a, b, c, d equals 0. So if this is the case, is this condition still satisfied? Well, yes, because a, b, c would be equal to 0, so a, b, c, a plus b plus c would equal 0. So this is satisfied. Then we have, if we have some existing ABC that satisfies a plus b plus c equals 0, so let's call this p of x with a capital P this time. And it's of this form. So let's just say that in this p of x, our a plus b plus c equals 0. Alright, so I had some technical difficulties, but what we were talking about was for p of x, we have this, let's say, p of x that's already within this subset, so it already satisfies p0 equals p1. So that means that for p of x, a plus b plus c equals 0. Now, what if we do c times p of x? Well, in this case, we have now c, I should put c, I should put a different constant. So I'll put f as our scalar that we're multiplying p by. So when we do that, we get f(ax) cubed plus f(b)x squared plus f(c)x plus f(d). Okay, so now we're going to see, is this in the subspace? So is this in, I guess, the I subspace? So that also basically means, does this satisfy the requirement that fa plus fb plus fc is equal to 0? So fa plus fb plus fc, is this equal to 0? Well, hopefully you can see that this is just doing f times a plus b plus c, which we already know is 0 because p of x is in 0. So this means that it is equal to 0. So our second closed under scalar multiplication requirement is satisfied. Now our third requirement is that it's closed under addition. So let's say now we have p1x equals a1x cubed plus b1x squared plus c1x plus d1. And then this is in the subset, so a1 plus b1 plus c1 equals 0. Because, right, the requirement of the subset is that it satisfies p0 equals p1, which means, again, that it needs to satisfy this condition. And then let's say we have another polynomial that also satisfies or is also in this subset. So a2x cubed plus b2x squared plus c2x plus d2. So that means because in the subset a2 plus b2 plus c2 is also equal to 0. So now our question is p1 plus p2 in our subset, so in the subset of 1. So when we add these two together, we get a1 plus a2 x cubed plus b1 plus b2 x squared plus c1 plus c2 x plus d1 plus d2. And is this in 1? So let me just write p1 plus p2 equals this. So to test that again, we check if the coefficients before the x cubed, x squared, and x terms, so in this case a1 plus a2, b1 plus b2, and c1 plus c2, if we add those together, does that give us 0? Because that's the requirement for this subset. C1 plus c2, is this equal to 0? Well, hopefully from here and from here you can see that we're just literally adding these two equations together in this equation. So then we just have 0 plus 0, which is equal to 0. And because we know this because p1 and p2 are already in the subset. So because of that, this is closed under addition. So because all three requirements are satisfied, so the 0 vector is in, it's closed under scalar multiplication, and it's closed under addition. This is a subspace, so 1 is correct. So that means we can eliminate D and E. And now we have 2. So 2, we have a set of polynomials in P3 satisfying P0 times P1 equals 0. So now our subset requirement is that P0, which is D from before, times P1, right? If we plug in 1 here, we get A plus B plus C plus D is equal to 0. So for this requirement to be satisfied, either D equals 0 or A plus B plus C plus D equals 0. So this is our requirement. And first we test if the 0 vector is in the subset. So when A, B, C, D are all equal to 0, this equation is satisfied because right, A plus B plus C plus D would just be 0, so 0 times whatever is just 0. Let's see. So this is satisfied. Second is if it's closed under scalar multiplication. So let's say, like here, we have our p of x equals to ax cubed plus bx squared plus cx plus d. And then we're going to see, so let's say that p of x is, so p of x is in the subset. And we're trying to see if f times p of x, so some scalar times p of x is also in the subset. So for p to be in the subset, right, it needs to satisfy d times a plus b plus c plus d equals 0. So if we multiply p of x by f, we get fa x cubed plus fb x squared plus fc x plus fd. Let's move this out. Okay. So now we're going to do this test to see if p0 times p1 equals 0. So that means is FD times FA plus FB plus FC plus FD equal to 0. And I think maybe I should clarify also that we get this from doing, right, P0 times P1. So, but in this case, if this is, I'll call this P2 of X, right? We're basically just doing P2 of 0 times P1, or P2 times of 1 is equal to 0. And that's how we get this expression. We're just making this our new polynomial that we're testing, and we're seeing if the P2 of 0 times P2 of 1 is equal to 0. And that's how we get this expression here. So, anyways, here you can see that this is just f squared times d times a plus b plus c plus d. And so because p of x here is in the subset d times a plus b plus c plus d is equal to 0, so that means that this is also going to be equal to 0 because we're just multiplying by a scalar. So this is correct. So it is closed under scalar multiplication. 3, we need to see if it's closed under addition. So, okay, so let's say we have again p1 of x, which is a1x cubed plus b1x squared plus c1x plus d1. And this is in the subset, so it satisfies the P0, P1 equals 0, which means that it satisfies d times a plus b plus c plus d equals 0. And there should be 1s on all of these. And then for P2 of x, same thing, but with different constants. And this one, it's also in the subset, so d2 times a2 plus b2 plus c2 plus d2 equals 0. Okay, and now what we're trying to see is p1 plus p2 in this subset. So we're trying to see this. And to see that, let's first add p1 and p2. So that gives us, it would be nice if I could copy and paste in PDFs, but we persevere. C1 plus C2 x plus D1 plus D2. Okay, so this is P1 plus P2 after combining, right, the coefficients. And we're wondering, does this satisfy A1 plus A2 plus B1 plus B2 plus C1 plus C2 plus D1 plus D2 multiplied by D1 plus D2 equals 0. Okay, so, alright, and so the way that we get this, again, the way that we get this expression is by doing P of 0, plugging that into here for x, and then doing the same thing with P1, which is going to give us this. So this is from P0, this is from P1. Okay, so the key thing here is that our requirement states that d times a plus b, so from here, d times a plus b plus c plus d is equal to 0. So this means that d is equal to 0 or a plus b plus c plus d equals 0, 0. So P1 and P2 can satisfy these requirements in different ways. So for example, in P1, maybe d1 is equal to 0. And then for P2, okay, so if d1 is equal to 0, then a1 plus b1 plus c1 could be anything, plus d1 could be anything. Right, so there's no restriction, because if d1 is equal to 0, then this requirement is going to be satisfied. In comparison, what if for P2 of x, a2 plus b2 plus c2 plus d2 is equal to 0? And then d2 could be anything, right? So if this is the case, then when we go over here, we look at a requirement, let's say that a1, okay, so let's say d1 is equal to 0. So this is a 0, and this is a 0. And then a2 plus b2 plus c2 plus d2 is equal to 0. So a2, b2 plus, oh, what happened here? C2 plus d2 is equal to 0. Oh, that's fine, but this is non-zero, so d2 could be anything. And a1 plus b1 plus c1 could also be anything. It could be, it doesn't have to be 0, right? Because our d1 is 0, so it already satisfies the requirement for p of 1. So in this case, you have just non-zero terms, so this doesn't necessarily have to be equal to 0. So because of that, it's not closed under scalar addition, or it's not closed under addition. So it's not a subspace. So 2 is not a subspace. And for 3, we have a set of polynomials with integer coefficients. So that is, okay, this is 2. And then we have 3 here. So let's say ax cubed plus bx squared plus cx plus d. And this time the only requirement is that they're integers. So first of all, 0 is an integer. So if a, b, c, d equals 0, then you're still going to have integer coefficients. So this is fine. If we have scalar multiplication, so okay, let's say that p of x equals this, and a, b, c, d are all integers. What if we have some scalar times p of x? That gives us like fa, like I've written before, plus fbx squared plus fcx plus fd. Okay, so are these coefficients integers? Well, not necessarily, because f is just a scalar, so f could be like 0.5 or 0.1 or whatever. It could be a decimal. And this means that fa, fb, fc, fd might not be integers. So in this case, it's not closed under scalar multiplication, so it's not a subspace. So this leaves us with A as our answer. And just to recap, what we did is we look at the requirement for each subset, and then we check first if the 0 vector gives us a polynomial that would satisfy this requirement. And then we also do the same thing for scalar multiplication, where we first make up a vector, or make up a polynomial in this case, that does satisfy this requirement. And then we multiply it by scalar, and then we check if if the resulting polynomial after the scalar multiplication also satisfies this requirement. And then we do the same thing with addition. We pick 2 polynomials that satisfy this requirement. And you don't have to actually come up with a polynomial, you just need to have the, this variable requirement down, because then you can just, for example, as we did here, write out this expression for the requirement. So we do the same thing, we pick 2 polynomials that are in the subset, then we add them together and then check if the resulting polynomial also satisfies this requirement. And if all 3 are satisfied, then it's a subspace. So hopefully that makes sense.
Okay, so in this problem, we have a differential equation, and we want to figure out what kind of point the origin is. So here you can see that we can write this giant matrix as x prime, where x is y prime, x prime and y prime. So this is like a big X. And this is equal to what I'll call this matrix A. So A times big X. And so as you can see, this is just a differential equation. And we want to figure out what kind of point the origin is, we want to find the eigenvalues, because that will give us information about what kind of point it is. So to find the eigenvalues, we're going to find a determinant of a minus lambda I and figure out when that is equal to 0. And I is just the identity matrix. This means we're going to do 1 minus lambda, 3, negative 2, and 2 minus lambda. And this is going to be equal to 0. This gives us the characteristic polynomial 1 minus lambda times 2 minus lambda plus 6 equals 0. And this becomes lambda squared minus 3 lambda plus 8 equals 0. So we want to now find the roots of that, and this means that we'll use quadratic equation, so 3 plus or minus square root of b squared, so 3 squared, which is 9, minus 4ac, so 4 times 8 times 1, divided by 2a, which is 2, times 1, which is 2. And so this gives us 3 plus or minus, so this is going to be a negative number. 32 minus 9 is 23. So let me write that better. Plus or minus square root 23, and this is going to be I because it's square root of negative 1, divided by 2. And so from this, you can see that the origin is, this is a complex eigenvalue, which means that the origin will not simply be an attractor or a repeller or a saddle point, because these would have not imaginary eigenvalues. So it's not any of those because it's imaginary, and it will be a spiral point because a spiral point, it represents an imaginary number. Or a spiral point corresponds to having imaginary eigenvalues. And another way of seeing like what the phase portrait will look like is we know that the general solution to an equation like x prime equals ax is some solution where x is equal to e to the lambda t, where lambda is your eigenvalue, times some constant, times your eigenvector. And you do this for all the other eigenvalues you have. In this case, we have 2, so we would just, our solution would be something like this. Right? And so you can see that even though this is imaginary, but the real part of it is positive, so we're going to have something going out from the origin, like this. But it will be in a spiral formation because it is imaginary. So our answer is D. Okay, so in this problem, we're trying to find which matrices are diagonalizable over the real numbers. So when we want to figure out which matrices are diagonalizable, you want to figure out, by definition, that if the eigenvectors of whatever matrix, so let's just call the matrix A, if those eigenvectors will form a basis for the vector space they're in, so r to the n. So for example, in this case it'd be r to the 2, this case it'd be r to the 3. And you also need to have, so if these eigenvectors form a basis for r to the n, they need to be linearly independent as well. And then we would, that means that we need n eigenvectors. Right, because for example, for 1, we are trying to span, our eigenvectors need to span r to the 2, so that means we need 2 eigenvectors. And then for here, we would need 3 eigenvectors that are linearly independent. And so to do this, we can do this step where we first find the eigenvalues of the matrix, and then what we're going to do is we need to find a basis for the eigenspace. So that means find the eigenvectors. And then the third requirement is that I don't know if this is, I don't really remember, but the algebraic multiplicity of the eigenvalue has to equal the geometric multiplicity of the eigenvalue. And so what do these mean? So the algebraic multiplicity means this is the number of times that you find lambda in the roots of the characteristic polynomial. And when we go through these examples, when we go through these actual matrices, it'll be more clear. And then the geometric multiplicity of lambda is the number of spanning vectors to the, maybe I should write it as number of spanning vectors in the solution to a minus lambda I x equals 0. which is essentially another word of saying the number of linearly independent eigenvectors you have. Okay, and this needs to be satisfied for all lambda. Yeah. Okay, so the way to do this, one way you could do this is actually employ this method, and we can do this an example for number 1. So what I'll do is first find the eigenvalues. So I do that by taking the determinant of a minus lambda I and setting it equal to 0, and then solving for lambda. So I have 2 minus lambda, -5, 3, -6 minus lambda equals 0, and that gives me lambda squared plus 4 lambda plus 3 equals 0. Okay, so now from this I can factor, and then I see that my eigenvectors are going to be -1 and -3. And now what I can do is I can solve for, wait, is this right? 12. Oh yeah, okay, never mind. We're good. So for the lambda of -1, I want to find the eigenvector, so I'm going to do a minus lambda I times x equals 0. So equals 0 here, and then 2 minus -1 is 3. I have -5, and then I have 3. -6 minus -1 is -5. So from this, I see that these two rows are linearly independent, and so my eigenvector, I can set that just to be 5 and then 3. So that's an example of one eigenvector. And then we check if the algebraic multiplicity equals a geometric multiplicity. So the number of times that we found -1 in the roots of the characteristic polynomial, which I think I should write out as this, that's going to be 1. And then the geometric multiplicity, or number of spanning vectors, is just going to be 1 as well, because we have one free variable in this column. So we have geometric multiplicity, and -1 is also equal to 1. And then for -3, I can do the exact same thing, and I'll get 2 minus 5, -5, 3, -3, 0, 0. And once again, I can find the eigenvector. It's going to be 1, -1. Wait, no, 1, 1. And so, obviously from this, you can see that the algebraic multiplicity is also 1 because it only appears once in the roots, and then the geometric multiplicity will also just be 1 because we have one free variable, and also we have one eigenvector that will span this eigenspace, so it will span the -3 eigenspace. So you can see that the algebraic multiplicity and geometric multiplicity are equal for all eigenvalues that we have, so 1 is going to be diagonalizable. So 1 works. So from that we can eliminate this one. Okay, so you could technically do that for all of these, but I think it's a bit tedious for especially 3 and 4 because now you have multiple, you're at a higher dimension, so it's just a lot more annoying. So the way that you can do this that is a bit easier is to figure out what the eigenvalues are. And if the eigenvalues all have algebraic multiplicity 1, then you surely will be able to find an eigenvector corresponding to it. So in this sense, you can actually shorten your approach a lot by just figuring out what the eigenvalues are and seeing if those eigenvalues all are different from each other. So I'll do an example now with 4. So with 4, I want to find the eigenvalues. So 7 minus lambda, 1, 1, 0, 2 minus lambda, 2, 0, 1, 3 minus lambda equals 0. And then I can just expand along this column, 7 minus lambda, and that is going to be times 2 minus lambda, 3 minus lambda, minus 2, and this is going to be equal to 0. And I can ultimately factor this out to get 7 minus lambda times lambda squared. Okay, so lambda minus 4 and lambda minus 1 equals 0. So you can see that my lambdas are all different, 4, 1, 7. So because we have unique eigenvalues, we are able to find at least one unique eigenvector corresponding to each eigenvalue. And this is just a quick trick to figuring out if a matrix is diagonalizable, because then you know that the algebraic multiplicity and geometric multiplicity will be the same for all these eigenvalues because they're unique. So hopefully that makes sense. I'm not actually entirely sure on the full logic behind that, but if all else fails, following this will certainly give you an answer as to if it's diagonalizable.
Okay, so afterwards I looked at why different eigenvalues actually give you, so when you have different eigenvalues, you will get linearly independent eigenvectors. And I found this, explanation in this textbook. So it's called Linear Algebra and Its Applications by Gilbert Strang. And it actually seems like a really good textbook, because I've actually used it a few times. But in this case, we assume, so let's say that we have, x1, x2 as our, maybe I should make this larger. Okay, so let's say we have, x1, x2 as our eigenvectors. And this corresponds to our eigenvalues, right? Lambda 1, lambda 2. So we can do the test for linear independence. So this means that, C1 times x1 plus C2 times x2 is equal to 0. And if these two vectors are linearly independent, then the only solution for this is C1 equals C2 equals 0. And so we know that, so we know because these are eigenvectors and eigenvalues, that ax1 equals lambda 1 x1, and ax2 is equal to lambda 2 x2. All right, so what we can do is we can multiply this by a, so multiply both sides by a. Then we get c1 times a x1 plus c2 times a x2 equals 0. And we know that ax1 is equal to this and ax2 is equal to this, so we can plug it in and get c1 times lambda 1 x1 plus c2 times lambda 2 x2. And okay, so this is equal to 0. Okay, so now I have two equations. Let me just... So now I have two equations. We have this as our first equation, this is our second equation. So what I can do is c1 x1 plus c2 x2 times lambda 2. This gives us, right, c1 lambda 1, or lambda 2 x1 plus c2 lambda 2 x2. And this is equal to 0 because we're just multiplying by a scalar. So this is equal to 1 times lambda 2. And from this we get, okay, so then we can also compare this with 2, right, which is c1 lambda 1 x1 plus c2 lambda 2 x2 equals 0. So we can just subtract these two equations and we get c1 times lambda 2 minus lambda 1 x1 equals 0. So because we've said that these are different eigenvalues, so they're distinct, and this is going to be non-zero, right? And this is an eigenvector, so it cannot be 0, right? Because Otherwise, if you have an eigenvector that's 0, then A times, your eigenvector times lambda times your eigenvector, that would just be 0, 0. So your lambda could be anything, which is not the definition of an eigenvalue. So you have to have a non-zero eigenvector. And so this means that this is non-zero. So then the only way that this can be 0 is if C1 is equal to 0. And you could make the same argument for C2 if we instead multiplied, for example, here we multiplied by lambda 2, but if we instead did 1 times lambda 1, you can get the same result and subtract again this equation from whatever you get here. And that should also give you that C2 has to be 0 for this to work. Alternatively, I guess you could just plug this back in here, and you can recognize that eigenvectors cannot be 0 vectors, so C2 has to also be 0. So because of that, because C1 and C2 are the only solutions, then we can verify these eigenvectors are linearly independent.
Anyways, so now we can go to 2. So on for 2, so we know that 4 and 1 are diagonalizable, so we can eliminate this one and this one. So for 2, find the eigenvalues, so 4 minus lambda, 1, 0, 4 minus lambda equals 0. So this means we have our lambdas are going to be, our eigenvalue is going to be 4. And this means it has algebraic multiplicity, not like that. Algebraic multiplicity of 4. Our eigenvalue is 2. Okay, and so now we're going to see if we can find 2 linearly independent eigenvectors. So when we subtract 4 and we find a minus lambda x, we get 0, 1, 0, 0, 0, 0. So our eigenvector has no choice but to be 0 and then some number here, so I'll just call it 1. So because we're restricted by this variable here, that it has to be 0, you can see that we only have one linearly independent eigenvector that can come from our eigenspace of our 4 eigenspace for this eigenvalue. So this means that if this is our only linearly independent eigenvector from this, because this is only one free variable, so we only have one spanning vector for this solution to a minus lambda ix equals 0. If you take that eigenvector, first of all, you can notice that it does not span r to the 2, so the eigenvectors does not form a basis for r to the 2, which means it's not diagonalizable. And the other thing you can note is that the geometric multiplicity of 4 then is equal to 1, which is not equal to the algebraic multiplicity, so that is false. So that means that 2 is not diagonalizable. So we can eliminate E, and then our answer is C. And just as a check, I'll again write that, so for 3, we can check to see if it is by finding the eigenvalues. The thing to notice about 3 is that you have I don't remember the term for it actually, but it's a kind of matrix where you have one side of it, so like this upper triangular half, you have non-zero values, or you have whatever values you need, but on the other side it's all zeros, so it's some kind of diagonal matrix. I don't exactly know what it's called, but you can figure out from that pretty quickly that your eigenvalues are going to be on the diagonal, so it's going to be 1, 5, and 7. And if you don't believe that, you can just expand, so you would get lambda minus 1 times lambda minus 5 times lambda minus 7 minus 0 equals 0. So then you would find the same thing, that your eigenvalues are 1, 5, and 7. So once again, our eigenvalues are unique, and that means that we will get at least one eigenvector for each eigenvalue, and that these eigenvectors will be linearly independent from each other. So that means that yes, this matrix is diagonalizable, and so our answer is again C. Okay, in this problem we have this real matrix A with eigenvalue lambda 1 equals 2 plus I, and the corresponding eigenvector. So we want to figure out which is the real solution to this system, and the system is x prime equals ax. So from problem 5, you might remember that the general solution for a differential equation like this is going to be x equals c1 times e to the lambda 1t times the eigenvector corresponding to lambda 1 plus c2, which is again some scalar constant that is defined by our initial conditions, but we don't really care in this case, but good thing to note. So e to the lambda 2t times the second eigenvector that corresponds to lambda 2. So this means that, okay, so for this problem, we know that lambda 1 is equal to 2 plus I, and v1 is equal to 3 minus I, and then 4 plus I. And a property of having complex eigenvalues is that your other eigenvalue is going to be the complex conjugate of your first one, and the same thing with your other eigenvalue, or eigenvector. So your second eigenvector is going to be 3 plus I and then 4 minus I. So what you can do is you can plug these in here and then using Euler's method, or was it? Euler's identity to make this into cosines and sines and convert everything. Or you can do maybe a more simple approach, which is, you know that, and I think you can prove this with a bit of algebra, but if you only look at this section, you can split this into the real and imaginary components, and those components will form your solution. So I'm going to do that method. It'll be more clear when I actually do it, but I think it's a bit easier than plugging both of these solutions in. So we have x equals c1 times e to the 2 plus it times 3 minus I and 4 plus I. Actually, I'm not going to use this x here, but I'm just going to plug these values in, and I'm going to use Euler's identity, so that means I get cosine 2 plus I times t plus, wait, what am I doing? Sorry, no, that's not right, okay. Okay, so this is c1 e to the 2t times e to the it times 3 minus I, 4 plus I. I'm going to do Euler's identity on this, and that will give me cosine t plus I sine t times c1 e to the 2t times 3 minus I, 4 plus I. And then I'm going to factor that, or distribute that out. So I get 3 cosine t, so I'm going to multiply this to the top one first. I get 3 cosine t minus I cosine t plus 3I sine t plus sine t. And then I get 4 cosine t plus I cosine t plus 4I sine t minus sine t. Okay, c1 e to 2t. Okay, and then my argument or the method I'm using is that if I factor this into the real components, so c1, 2t, so I get the real components, which is here and here, those 3 cosine t plus sine t, and the real parts from here, which is 4 cosine t minus sine t. And then I should probably make this different. So let's do c3 times e to the 2t plus c4 times e to the 2t times, now I'm going to use the imaginary part, which is negative cosine t here, plus 3 sine t from here, and then cosine t, this one, plus 4 sine t from here. So this is actually a solution to the differential equation. If I only just split things up into their real and imaginary components. And I take the real part and the imaginary part as my two solutions. So this is a valid solution for this differential equation. And I think it's a bit easier than plugging in both of these and doing the math, because it results in pretty much the same thing if you're trying to find it as a real solution. So looking at this, that means 3 cosine plus sine t. So these aren't right because these are wrong. And then the difference between these last two is the sine. So we want 3 sine t minus 2 cosine t, which is this. So our answer is E. Okay, in this problem we have this transformation of a 2 by 2 matrix to the same 2 by 2 matrix, which is going to be A plus A transpose. So what that means is this is our A and this part A. So we're trying to find a transformation of this matrix. So what we're going to do is that we're going to just do A plus A transpose, which is equal to 1, 2, 3, 4 plus transpose this, which is 1, 2, 3, 4. That gives us 2, 5, 5, 8. So that is a transformation. In part 2, we have finding a basis for the range of t. So this is asking us to find the span of A plus A transpose. And that means we're trying to find we want to find a way to express all A plus A transposes in the simplest form possible. So what I'm going to do is I'm going to make up my initial matrix, my initial 2 by 2 matrix, to be A, B, C, D. And then I'm going to do the transformation. So the transformation of A, B, C, D is equal to the initial matrix A, B, C, D plus the transpose, which is A, B, C, D. And I get that. I get 2A, B plus C, B plus C, and 2D. So this represents all the possible matrices, 2 by 2 matrices that you can get from this transformation. Now I'm going to decompose this to find the basis. So I can do 2A times 1, 0, 0, 0, because these other 3 entries don't have A in it. I'm going to do plus B times 0, 1, 1, 0, plus C times 0, 1, 1, 0, plus 2D times 0, 0, 0, 1. So that is equal to this decomposition. And as you can see here, we have 3 linearly independent vectors. So these will form the basis for the range of t. And this means that a linear combination of these 3 vectors can form all the possible transformations. So our basis is this. Right, because these two are obviously the same, so we don't obviously include them twice. Okay. In part 3, we're trying to find a basis for the kernel of T. The kernel in this case is essentially asking for a null space of your transformation, which is A plus A transpose. So this means that whatever transformation we're doing, we're always going to be transforming the initial A matrix to 0. So one way you can do this is to literally go 2A, B plus C, B plus C, 2D, and I'm taking that from up here, equals to 0, 0, 0, 0. And if you do the matching, obviously A and D have to be 0, so there's that. But then we also have a condition that B plus C is equal to 0. And so if we want to find what our basis is that will describe all the transformations that go to 0, then we need these conditions to be satisfied. And so our basis can be written as A, B, C, D, but it's going to be 0, 0 on the diagonals because A and D are equal to 0. And then B is going to be equal to negative C, so we can just have negative C, C here. And this is going to be all our A matrices that will satisfy this mapping. Hopefully that makes sense, because if you look up over here, if we have, A equals 0 and D equals 0, and then B is equal to inverse of C, or not inverse of C, that B is the negatives of C, you would get something like B times 0, 1, 1, 0 minus B times 0, 1, 1, 0, which would just be 0. So that would always map you to the 0 vector. So these are the conditions that we need to uphold, unless A can be anything of this sort. And if we factor this out, we get C is equal to 0, negative 1, 1, 0. And so this vector here is going to be our basis for the kernel, or the null space, of A plus A transpose. And another way of thinking about this is looking at this equation of here. You can see that if we were to write this, so let me do this. So if we have this equation, we know this is going to describe our transformation. If we want to set this equal to 0, 0, 0, 0, you can write this as actually a form of a system of equations. So this would be 2a plus 0 plus 0 plus 0, and then equals 0. Same thing on the top right corner, 0 plus b plus c plus 0 equals 0, and then 0 plus b plus c plus 0 equals 0, 0 plus 0 plus 0 plus 2d equals 0. And you can actually write this in the augmented matrix form, which is 2, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0, or 2. Because in this case, we're just describing this matrix as, some matrix here times A, B, C, D equals 0. I'm going to mark this one as alternative way of doing things, because this would be helpful when equations are more complicated. So we have this system, and you can just row reduce this, right, to get 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. And this will again give you the exact same information, so A equals 0, and D is also equal to 0. And then B is equal to negative C. And from that, you can see that the same logic applies, where if you decompose the initial matrix A, B, C, D, then you get a system in this form. And so you get an expression in this form. And so the basis that describes the matrix that will be transformed into the 0 vector through this transformation is going to be this matrix here. Okay, in this problem, we're trying to find the eigenvalues of this matrix and a basis for the eigenspace corresponding to the eigenvalues. So, basis for eigenspace is pretty much asking us to find the eigenvectors, because this will span, the eigenspace is spanned by the eigenvectors. So, the first thing to do, to find the eigenvectors, we find the determinant of A minus lambda I, where I is the identity matrix, and we set that equal to 0 and solve for lambda. So when we do that, we get 4 minus lambda, 0, 0, 1, 2 minus lambda, 1, negative 1, 2, 3 minus lambda, and that equals 4 minus lambda. I'm going to expand along this top row because I have zeros here, which will make my life easy. And so that gives me 2 minus lambda times 3 minus lambda minus 2, which is, let's see, so this is lambda squared minus 5, lambda plus 6 minus 2. So I can factor that into 4 minus lambda times lambda minus 1, and then lambda minus 4. This means that my eigenvalues are going to be 1 and 4, where 4 is a repeated eigenvalue. Okay, so now we need to find the eigenvectors, and to find the eigenvectors for each eigenvalue, we want to figure out what a minus lambda x equals 0, and we want to solve for ax that sounds confusing. We want to find an x that will satisfy this equation, and that is our eigenvector. So we plug in that, so we get 4 minus 1, which is 3, 0, 0, 1, 2 minus 1, which is 1, and then negative 1, 2, 3 minus 1, which is 2. And this is going to be equal to 0. Now, I'm going to row reduce this. What I'm going to do is I'm going to do row 2, or I'll do row 3 is equal, well, I guess it doesn't matter, but row 3 is equal to row 3 plus row 2, which is, so I'm going to do also row 1 is equal to row 1 divided by 3, gives me 1, 0, 0, 0, 0, 0, 0, 3, oh wait, I did it to row 3, not row 2, okay, 1, 1, 1, and then 0, 3, 3. And in short, you can see that I can divide this row by 3, which will give me 0, 1, 1, and then I can subtract this row then from the second row. So when I do that, I'm not going to write this out explicitly, but hopefully you can see that it will become 1, 1, 1, 0, 1, 1, which then I can subtract the second row from, I can subtract, okay, actually I'll just write this out, I think it's easier that way. So I'll do row 2 equals row 2 minus row 1 minus row 3. And this gives me a row of zeros, so I'll switch that to here. And this is what I end up with the zeros here. And so from that you can see that we can express the x1, x2, x3 as this first pivot entry tells us that x1 is equal to 0. And then we also see from this expression, this relation, that x2 is equal to negative x3. So we can write that as 0, 1, negative 1. This will give us our eigenvector corresponding to lambda equals 1. These are our eigenvalues. Okay, so that is for lambda equals to 1, and now we're going to go to lambda equals 4. Same process, so 4 minus 4 is 0, 0, 0, 1, negative 2, 1, negative 1, 2, 3 minus 4, which is negative 1. So this one is a lot quicker because you can see that this automatically, you can do third row plus second row, which will give you a row of zeros. So our only relevant stuff is 1, negative 2, 1. Okay, so this gives me x1 minus 2x2 plus x3 equals 0. And I want to find what this x is that will give us this expression. That will be our eigenvector. So the first eigenvector that I can come up with is, maybe I'll set x3 equal to 0, and then I can make x2 or x1 be equal to 2 and x2 be equal to 1. So this satisfies this equation if you just plug in the numbers. And what I want to do is I want to find a second eigenvector that is linearly independent to this one we just found, because I want to have one eigenvector for each time I want to have one linearly independent eigenvector for each time the eigenvalue it corresponds to is repeated. So I want to have two linearly independent eigenvectors. And this is pretty easy to do because I can just move the 0 to another place. So I can make x2 0 here, and these won't be multiples of each other.
which means that they're going to be linearly independent. So if I do that, I can have, I can make x3 1 and then x1 -1, and that will satisfy this equation. So now I have these two linearly independent eigenvectors that correspond to lambda equals 4. And that's going to be the basis for the eigenspace. So the basis will be v1, v2, and v3. Okay. Now I'm going to find an invertible matrix P and a diagonal matrix D such that that they can be written to get this matrix, which is A up here. Okay, so the first thing to realize is if I multiply both sides on the right by P, I get AP equals PD. And what ends up happening is this invertible matrix P is the eigenvectors. So the columns of P are going to be eigenvectors. So I can write this as P1, P2, P3 for this case, where P1, P2, and P3 are eigenvectors. And D is a diagonal matrix with lambda 1, lambda 2, lambda 3, and all the other entries are zeros. So all the entries that are not on the diagonal are 0. And the important thing to realize is that these have to correspond. So the lambda 1 has to correspond to P1, the lambda 2 has to correspond to P2, and lambda 3 with P3. So those eigenvectors must correspond to the right eigenvalues. And just as a quick little theory part where you can kind of, this isn't really theory I guess, but you can kind of understand how this happens, because if I substitute in the P1s, so A times P2, A times P3 equals P times D, which will just be lambda 1 P1, lambda 2 P3, and lambda 3 P3, where I just substitute it into this equation here. You can see that this is equal to this, and this is the exact definition for finding an eigenvector and for an eigenvalue. So this should intuitively kind of make sense. So this should make sense with the math that we have up here. So this should make sense with the A equals PD times P inverse, because you can see how the eigenvector definition is found from this expression. So anyways, what you can do is literally just put down your eigenvectors. So we have, so we're going to have our first eigenvector be V1, then I'm going to do V2, 2, 1, 0, and then V3, -1, 0, 1. And then D has to have the lambdas correspond to the eigenvector. So V1 corresponds to the eigenvector of 1, or eigenvalue of 1. Then lambda 2 and lambda 3 are both going to be 4, which correspond to these two eigenvectors. And everything else is zeros. So this is an example of an invertible matrix and a diagonal matrix that does satisfy this expression. And of course, you can have the columns be switched around. So if I did, like, say, 2, 1, 0, 0, 1, -1, -1, 0, 1 for P, but I had to now make sure my diagonal matrix matches up. So this has to be 4, this has to be 1 now, and this is 4 still. So just be careful to make sure that your diagonal matrix and your invertible matrix P lines up. You can also check by literally finding P inverse and then plugging it in to here and seeing if it equals A. So if A is equal to PD. So you can do this as a check as well. Okay, in this problem, we're trying to find the eigenvalues and eigenvectors, so hopefully by now we're more comfortable with this. So to find the eigenvalues, I find the lambdas where the determinant of A minus lambda I is equal to 0.
So that means negative 5 minus lambda, 1, 4, negative 2 minus lambda. Find this determinant. So that I get negative 5 minus lambda times negative 2 minus lambda minus 4 equals 0. I get lambda squared plus 7 minus 10, plus 10 minus 4, which is plus 6, equals 0. So then I factor that out and I get lambda equals negative 1 and negative 6. Now I can find my eigenvectors by doing lambda equals negative 1 by plugging it in to find when the x where a minus lambda I x equals 0. So this will be negative 4 now, 1, 4, negative 2 minus negative 1 is negative 1, equal to 0. So you can see that these are multiples of each other, so one solution x1, x2 that satisfies this expression will be if x1 is equal to 1 and then x2 is equal to 4. So this is our first eigenvalue, and that corresponds to lambda equals negative 1. I can do the same thing now for lambda equals negative 6, and that will give me 1, 1, 4, 4, 0, 0. And this means that I can pick x1, x2 to be, you can see that again these are multiples of each other, so x1 and x2 need to satisfy the x1 plus x2 equals 0. So I can pick x1 to be 1 and x2 to be negative 1 to satisfy this. And the same goes up here, right? So if we have negative 4x1 plus x2 equals 0, this will satisfy this expression. Cool, so this is going to be our second eigenvector that corresponds to lambda equals negative 6. Okay, now I want to find a general solution to this system of differential equations, which this is going to be equal to a. Oh, that's a bit annoying to have it there. Okay, so there. And to find this general solution, we know that the general solution to some expression like this is going to be some c1 times e to the lambda 1t times your eigenvector, which is in this case v1, plus some scalar constant e to the lambda 2t. Lambda 2 is your second eigenvector, or eigenvalue, and I should write this like here. Okay, so this is going to be the general solution to a system that is in this form. So good thing we already have all our eigenvalues. So we have c1 e to the negative t times 1, 4 plus c2 times e to the limit 2t, which is negative 6t, times 1, negative 1. So this is going to be our general solution. So this is the big X that I'm going to denote as x, y. So this is our general solution to this system. Okay, so now we have x and y being a particular solution to the initial value problem shown here. So we already have our general solution, so this means we're just trying to find what c1 and c2 are based on this initial condition. So we can plug in x0 and y0, so t equals 0. This gives me, so I'll just write this out explicitly, x0, y0 equals c1, so e to the negative 0 is 0, so c1 plus c2, so e to the negative 0 again is 0, and then I'm going to have 4c1 and minus c2. And I just got that from plugging it in and then adding the entries in the corresponding row. So this is equal to 3, 7 from this information here. So if we just add these together, so this is a system of equations, c1 plus c2 equals 3, 4c1 minus c2 equals 7, And if I add these together, I get 5c1 equals 10. So c1 equals 2. And that means c2 is equal to 1 if I just plug it back in here. So this is what our constants are going to be. So now I want to find x1 plus y1. This means we have, so our x is our x1, y1. So x1, y1 equals c1, which is 2, e to negative 1. Oh, oops. Let me just do that real quick. Okay. E to negative 1 times 1, 4, plus c2 is 1, so 1 times e to negative 6 times 1, which is negative 6, times 1, negative 1. And this will give us 2 times e to negative 1, 8 e to negative 1, plus e to negative 6 minus e to negative 6. Cool. So now if we do x1 plus y1, we get 10 e to negative 1. And that is our answer. So I think that's the end of the exam. So, yeah.